Hi there. Thanks for joining us on another episode of Space Nuts. Andrew Dunkley here, and it's good to have your company. Coming up on this episode, we're going to be looking at Snowball Earth. There was a time where it was just a frozen sphere of nothingness for, well, billions of years. Now they have a new theory about that, and it's no Irish joke. There's a clue in there. The Dinosaur Asteroid's origin has been revealed. Yep, the thing that started the getting rid of them all across the planet. We know where it came from. And the so-called crisis in cosmology might not be a crisis at all. We're talking about the Hubble tension. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And to help us unravel all of that, decipher it, and use his code book to figure a few more things out is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Keep up the good work there. It's going very well.
It's good to see you. Now, I thought I'd sort of start out of left field because I spotted a story only today, actually, which dovetails with something we talked about some time ago, and that was the work that's being done to perfect engine technology to achieve greater speeds for interstellar travel in years to come, or maybe not interstellar, but interplanetary perhaps. And we know NASA is working on this kind of technology to create really fast and high-performance engines. They're working with, I think it's General Electric to achieve that. They may have been gazumped, Fred. Have you heard about this?
No.
The Chinese claim to have developed a new engine that can achieve a speed of 12,000 miles per hour, or 19,700 kilometers an hour. And the aircraft can reach an altitude of 30 kilometers. Now, you compare that to the Concorde, it's Mach 16 versus Mach 2, which is an extraordinary claim. Now, apparently they've released a paper which has been peer-reviewed, from what I understand, and it's not April the 1st. I'm confident of that. So they reckon that they've made this leap in technology to develop a Mach 16 engine. And just think of this, Fred, you'd be able to fly from Sydney to New York in 50 minutes.
Yes, that's right.
50 minutes. That's extraordinary if it's real, and I don't see why it wouldn't be, but you never know with these things. But apparently, according to the paper, the engine operates in two modes. There's a continuous rotating detonation engine, which is a scary thing in itself by the sound of it, which will get it to Mach 7. And, the air and the fuel create a rotating shock wave with continuous thrust. And then a straight line oblique detonation engine, which fires above Mach 7 and pushes it all the way to Mach 16. It sounds amazing. How far short they are of getting this into production, I don't know, but it certainly sounds like it's in development. That would be amazing to be able to achieve those kinds of speeds. It would revolutionize travel around the world.
But it's been done already. The British have been working on this for decades now with their it's an air-breathing, it's a hybrid engine that breathes air at low altitudes and turns into a rocket motor when you get above the Earth's atmosphere.
Yeah, I think I did hear about that. I didn't know it got to those sorts of speeds.
Yeah, well, it's capable of entering orbit, so it can get up to 26,000 kilometers an hour. But it's then acting as a rocket motor. So it's the project was called, HOTOL was the style of thing, horizontal takeoff and landing. So it flies like a plane, takes off like a plane with the air-burning jet engines, just gradually accelerates, clicks over into being a rocket motor when the atmosphere gets too rarefied, and then sends you up to orbit. But as I remember right, I think it's called the Sabre, the engine. If I remember rightly, it's the Sabre. But the big problem was keeping the air cool. And there was the main breakthrough was apparently a heat exchanger that could bring the temperature of the air down from 700 degrees Celsius or something to liquid nitrogen temperatures in something like 1,000th of a second as it passes through the engine. And that was a big breakthrough. Now, I think we've spoken about it before a long, long time ago, because there hasn't really been much news. It was being supported by the British government. I don't know whether that support has now dwindled. Because it would be, the idea about this was economics. It was to be able to have the same spacecraft that will take you up there and bring you back, and was completely reusable. And to some extent, I think Elon Musk's SpaceX and their Falcon 9s have kind of cornered the market on that, because they've now got reusable spacecraft which are routinely being used every day almost. So maybe there's no space for it. But yeah, it's extraordinary technology, and I'm sure the Chinese technology is above board, what you've just been describing.
Yeah, it's from the Beijing Power Machinery Institute, and they've published their paper in the Chinese Journal of Propulsion Technology. Yeah. I can see a problem with it, though. Let's say they do create an airliner that can do that trip in 50 minutes from New York to Sydney, for example. You'd leave at 7 o'clock in the morning in New York. You'd arrive at 11 p.m., 50 minutes later in Sydney. So you'd get up and get on the plane, then get to Sydney, and then have to go to bed wide awake.
Yes. That's right. That's the issue. It's always the issue.
It would make jet lag all the more worse.
Yeah. But, I think I'd put up with that rather than have all those
20 hours. 20-hour flight. Yeah, I've got one of those coming up very soon, actually.
You do? That's right.
Yeah, it'll be to watch this space story, but I just find it fascinating, these kinds of leaps in technology. Let's move on. A new theory about Snowball Earth, Fred. I said there's no Irish joke attached to this, and there's a good reason I said that.
Which I'm probably going to sidestep completely. It's about rocks in Scotland and in Australia.
I thought they said there was some of these rocks in Ireland as well.
Yeah, I think there are. I think that's right.
I think that's the loose connection I made with it.
It also includes rocks in Namibia and North America, as well as Scotland. You're probably right, in Ireland, because it's the west of Scotland where these rocks are that have recently been analysed. And it's an interesting story. I've often wondered about Snowball Earth. I never really looked at the details of it. So it's a period of about 60 million years ago. 60 million years long, but it was a long time ago. It began 700 million years ago. In fact, probably more like 720 million years ago, and lasted until about 635 million years ago. And it's called the cryogenian geological period, and anything with cryo in the front of it means it's frozen solid.
Yeah.
And so I thought, well, how do we know this? And the way we know it, and the way we know that glacial ice covered the whole planet, is because you can see in the geology the effects of glaciation everywhere. It's not just, I grew up in a country where 10,000 years ago, the whole of the northern part of Britain was under ice. And so all my school lessons were about glacial features in the north of England. And so you can tell from rocks whether something has been glaciated. And that's how we know everywhere there is this layer of rock corresponding to looking back, 600 or 700 million years, where you see the evidence of glaciation. And so the interpretation of that is that you had an ice age that was if I put it, the grandfather of all ice ages. The whole planet was frozen. And so the new research concerns evidence from rocks in Scotland. And what's remarkable is that the sort of glacial evidence there shows up really clearly. For some reason, that has been preserved very well there, underneath the sediments that were dropped on top of on top of it later on. But the bottom line about the reason why we got this ice age is a question. I'm not sure that in the article I sent you it goes into detail about it, but the thinking is that we were seeing a period when, or before this period, we were seeing a time when volcanic rocks were being eroded. They were being weathered very rapidly, and apparently these were particularly in Canada. These volcanic rocks, I'm looking back now, perhaps 720 million years, they were eroded by weathering, and that process sucks carbon dioxide out of the atmosphere. And so what you're seeing is a situation where the atmospheric carbon dioxide is lower than normal. And in fact, it was probably about half what today's level is. Today's level's in the region of 400 parts per million of carbon dioxide in the atmosphere. And that's enough to blanket our planet and keep the temperature stable, unless you put more in which case the temperature goes up, as you know. But if you drop too far down, then you get an ice ball. They estimate the atmospheric carbon dioxide levels back in the cryogenic period or cryogenian period. They estimate they were below 200 parts per million. And what that does is lets the heat just radiate out into space, and you lose heat. The Earth's surface becomes very cold, and basically you get the Snowball Earth. You get an Earth that is covered with ice. It's the same sort of thing that we think happened on Mars. Mars has very low carbon dioxide content, and that's why we think it got cold and dry rather than warm and white as it once was.
There's a lot of moving parts to this story, but one of the things I found most interesting was that if this mega freeze hadn't happened, life as we know it may not have developed. Because up until this time, it was just microbial, that was it.
That's correct. And the thinking, yes, it was single-celled organisms until that time, and they were around for 3 billion years or so. Nothing happened except these single-celled organisms, principally cyanobacteria. They just did their thing and got on with life, but didn't evolve in any way. But the end, this end of the glacial period, was such a sort of rapid climate change by the standards of the time, by geological standards, that the thinking is that you'd got almost an arms race to adapt to this new situation where the microbes are not permanently in deep freeze. You've got a warming climate, and the evolution of the microbes kicks in at a much higher level than it was before. And that is where we think that the multicelled organisms started to be formed, and that's what are the ancestors of all the animals that we see today.
Yeah, so basically those who survived the thaw or adapted to it created life as we know it. Yeah, that's just extraordinary sort of factor to come out of it. The other thing correct me if I'm wrong, but these rocks we were talking about in Ireland and Scotland and Australia and everywhere else, the reason that these are so different is I believe these were rocks that actually stuck out of the ice. Is that correct? During that freeze period?
They may have done, or at least been subject to less glacial activity. So yes, they may have had only a thin layer of ice over them rather than be under kilometers of ice. So I think you're right there. And just to confirm, you're quite right that some of these rocks are in Ireland as well. I hadn't spotted that, Andrew, in my reading of the paper. But yes, so you've got, particularly, you've got these rocks on some of the Scottish islands. These are small islands called the Gavellas. And it's basically in the west of Scotland. It's under the Portaska Formation. This is a geological area, Portaska, very well known to Scots people because it's the name of a well-known pipe tune. So let me quote from one of the authors of this work, and he's actually a PhD candidate at the University College London. The layers of rocks exposed on the Guyvelis are globally unique. Underneath the rocks laid down during the unimaginable cold of the glaciation are 70 meters of older carbonate rocks formed in tropical waters. These layers record a tropical marine environment with flourishing cyanobacterial life that gradually became cooler, marking the end of 1 billion years or so of a temperate climate on Earth. Most areas of the world are missing this remarkable transition because the ancient glaciers scraped and eroded away the rocks underneath. But in Scotland, by some miracle, the transition can be seen. And I think that's underlining what you said. They were either sticking up through the ice or they weren't particularly deeply covered by ice. So it's minerals and radiometric dating of the minerals that have allowed this discovery to be made.
Yeah, it's incredible, isn't it? All the answers are right there in front of us in the dirt sometimes. Simple as that.
Yeah. That's how we know so much about the history of not just our planet, but the other planets of the solar system. Just learned from looking at the rocks. That's right.
Yeah, fantastic. If you'd like to read the article or chase up that story, it's on the cosmosmagazine.com website. This is Space Nuts. Andrew Dunkley here with Professor Brad Watson.
Roger, you're loud and clear here also.
Space Nuts.
Speaking of dirt, Fred, we've got the dirt on the Dinosaur Asteroid. We now know, thanks to a new study, where it came from. This is fascinating too.
It is, that's right. And, it's not that long ago that people were really still speculating about where the remnants of this asteroid was. We're now pretty certain that it's in the Chicxulub Basin in the Gulf of Mexico, that is the site which actually was the impact site of this asteroid. So what you can do is you can look at the rocks that you find in that region. Once again, we're looking down at the dirt, and but basically look to see whether we know of anything like it out there in the solar system. And the bottom line is that yes, we do find that. In particular, and this is work being done at the University of Cologne in Germany, the element ruthenium is basically a chemical marker, if I can put it that way, that is found in the debris around the Chicxulub impactor and apparently in other sediments around the world, because the debris from that explosion spread all around the world. It was so, such a major piece of explosive material. It was only explosive because it hit the ground at a very high speed, probably 30 or 40 kilometers per second. But the fingerprint of ruthenium has been found in that debris. And it turns out that coincides with rocks in the main asteroid belt. That's the region between Mars and Jupiter, but at the outer edge of the main asteroid belt. Not the kind of place you'd expect. You would think if that rock had come from the asteroid belt, you'd think it would be near the inner edge, but the chemical specifics tell you that it's actually at the outer edge. And that is really a very, very interesting deduction. Who would have thought that we would be able to pinpoint where that asteroid came from 66 million years after the event? Maybe the asteroid...
I guess they worked it out on the chemical composition elements rather than backtracking.
Yes, that's right. We don't have enough information to backtrack. We don't know what angle it came in at, or what its orbit was before it collided with Earth. So it's all about chemistry, is this, and in particular some quite sophisticated. Well, I suppose you call it chemical physics, because they're using radiation techniques basically to look for these levels of ruthenium in the debris from the asteroid crater and surroundings, and basically, looking at how it compares with other asteroid impacts and carbonaceous meteorites, which also come from that region of the solar system.
So what might have caused a rock from that particular part of the solar system to, turn its attention to us? Did Saturn get upset and chuck a rock at us or something?
It's probably just a gravitational disturbance, something that disturbed the orbit of this asteroid in its comfortable zone of the asteroid belt, maybe an interaction with another asteroid, because when objects come together, they needn't necessarily collide, but if they can interact with each other gravitationally so that one of them gets thrown out of its orbit, and it's possible that would have been the case.
It's kind of like being in a crowd at a Chinese supermarket, really. That's what it's like.
Yes.
You didn't want to go that way, but you ended up going.
You have to go that way. Yeah, just because everything's so crowded. It's a bit like that. The thing is that event, whatever tipped it out of its comfortable orbit, that might have happened a long time before the 66 million year date ago that we have for the impact, for the extinction of the dinosaurs. So it might have been in an orbit that intersected the Earth's orbit for a long, long time before the crunch finally came, when it tried to be in the same place at the same time as the Earth. So there's details for this story that we still have a long way to finding out. But it may well have been, as I said, it's either a collision with another asteroid, or maybe even something like the gravitational pull of gas giants. Maybe Jupiter perturbed that object's orbit in such a way that it interacted with another asteroid and got thrown out of the asteroid belt. We probably will never know that. It's interesting enough, I think, to discover whereabouts it came from.
Yes. The other thing that came out of this is that it all but writes off that this was a comet impact.
Yeah.
But not absolutely.
Yeah, that's right. There's still a possibility, but comets are a different beast from asteroids. They contain lots of ice as well as the rock, and that means that the chemistry of the residual material from the impact would have different properties. So I think it's you can never say never, but the body of opinion seems to be that it was actually an asteroid rather than a comet.
Yeah. I do have just one more question about this story, and this is the most important one for it. Most important. You mentioned the element ruthenium.
Yes.
So was the person who discovered that named Ruth?
That's a good question. I'd have to take that one on notice, but my guess is that that's where the name came from. Or
I was wondering that.
Maybe it was somebody who was ruthless.
Oh.
And they thought, I'll call it ruthenium because I'm ruthless. Who knows that?
Yeah. That's a thought too. That story, if you would like to read it, is available at space.com.
This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, to the so-called crisis in cosmology. We're talking about the Hubble tension. Now, we've done this story a few times over the years. This is where basically the expansion speed of the universe, depending on how you calculate that number, comes up with two different answers, and they've never been able to figure out why. But now they're starting to think, well, there's no crisis at all. Everything's right.
Yes. So let me just explain how this tension, the Hubble tension, comes about.
Yeah.
Because there are two ways of measuring the expansion of the universe. One uses standard candles, and the other uses a standard ruler. and put it that way. So the standard candle's taking that first. If you know how bright your candle is, then you can work out how far away it is from you, because you know its real brightness, its intrinsic brightness. Then you can work out what is going on in terms of, because we know the way light gets fainter. We know the rule by which light gets fainter as you move to greater and greater distances. It's what's called the inverse square law. It goes as the square of the distance, or 1 over the square of the distance. So standard candles are usually stars in galaxies. And in fact, this is what led us to detect the expansion of the universe in the first place, because in the early years of the last century, around 1900, a group of astronomers in the United States measured the intrinsic brightness of a particular kind of variable star, one whose brightness varies, but it varies in a periodic way. And it turns out that there's a relationship between how frequently it varies and what the intrinsic brightness is. And you usually take it at peak brightness or minimum brightness, whichever. It doesn't really matter as long as you know what it is. And so that's the time-honored way of working out how far away galaxies are, to look for these variable stars and then basically look at how bright they look to us, and from that work out the distance. And that lets you produce a value for what we call the Hubble constant, which is the number that basically tells you how fast the universe is expanding. The Hubble constant is in units of kilometers per second per megaparsec, but we don't really need to worry about that, because at the moment all we're interested in is the number. And so until now, the best estimates from the standard candles, in other words, the Cepheid variables, have come out at about 74 kilometers per second per megaparsec. But then the standard ruler method is looking back at the flash of the Big Bang, the cosmic microwave background radiation, which we see as it was about 13 billion years ago. And there are features in that variation which have separations that we know would be characteristic of a certain particular time. And what we're talking about here when I say features, I mean peaks and troughs in the temperature of the Big Bang, effectively what you're looking at. And from that, you can also deduce the Hubble constant, the expansion rate, as it is today. But the answer you get from that is 67.5 kilometers per second per megaparsec, which is round about 6.5 kilometers per second per megaparsec, different from the other one. And that is now, we're in such a precise era that now has people worried. So what's happened? Well, the same team who've done a huge amount of this work in the past, led by Dr. Wendy Friedman, one of the big names in this kind of science in the United States. Wendy and her team have used our new toy, the James Webb Space Telescope. We always knew it would solve this problem. We knew it would certainly help. It would either make it worse or it would solve it. And you're right. To cut to the chase, it's probably solved it, because it's now looking as though the method is more like the method where you measure the brightness of these variable stars is giving an answer more like 70 kilometers per second per megaparsec, which is much closer to that 67.5 that you get from the cosmic microwave background radiation. And it turns out that when you think about the error, potential error of both of them, then it overlaps. So in that regard, you've got something that falls within the error bounds of both of these methods. And so maybe we are seeing the right answer at last. So it basically brings it back to an average. That's right. That's both methods. Yeah. Yes. Yeah. When I started my career, Andrew, there were two camps, and basically they were using similar methods. One said that the Hubble constant was 50 kilometers per second per megaparsec. The other said it was 100 kilometers per second per megaparsec, and they were both right. They thought they were both right, and it turned out that the real answer was the average of them. It was 70 or 75 or thereabouts. There you go. Pretty simple solution at the end of the day, but a lot of hard work went into finding it. And we hope that resolves the Hubble tension. It would be great. Hopefully, cosmic crisis disappeared.
Yeah, I wouldn't be surprised, though, in months to come, somebody comes up with a debunking theory.
Well, there you go.
It could happen. It could happen. But at this point in time, looks like it might have been resolved. This has been frustrating for a long time, but may be as simple as, oh, hang on a sec, you're both right, and here's why. That story's on scitechdaily.com. Question without notice, Fred, that's come through from one of our live viewers, Wayne. Hi, Wayne. This harks back to the Snowball Earth story we did. Wayne asks, I wonder how much bigger the diameter of a frozen Earth would be to the current Earth. Do we have any idea what that might have been?
Yeah, it probably wasn't that much different. You know, I mean, at the moment, a lot of that water's still there, but it's wet. And you know, and this is now it's turned into ice. So it's not going to be. It's certainly not going to be tens of kilometers different. It might be a few kilometers different on average, and I'm talking about the average. But I don't think it would. You know, it wouldn't have turned into a gas giant or anything like that. It's an interesting question, though, because we think it's because of frozen water out in the depths of the solar system, adding to the mass of the gas giants as they were being formed. We think that is one reason why they became so big, because they had enough mass to hold on to a gas envelope. And so it's a good question to ask that. What difference would the ice make? But this is really just a surface layer of ice rather than a solid block of ice, which may be at the core of the gas giants.
Indeed. All right. Thank you, Wayne. Nice to get questions without notice while we're going out live during our recording sessions. Good to hear from you. Fred, we're just about done. Thank you very much.
A pleasure, Andrew. Good to talk, and some interesting topics, and there'll be more next week.
Indeed, there will. Thanks, Fred. Professor Fred Watson, astronomer at large. Don't forget to check us out online, spacenutspodcast.com, spacenuts.io, where you can check out the shop, maybe become a supporter of the podcast if you're interested. Just have a bit of a flick around. And if you follow us on social media, don't forget to like us, follow us, add us to your favourites list, or click the subscribe button, depending on which platform it is. And thanks to Hugh in the studio, as always. And from me, Andrew Dunkley, we will see you again soon on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.